think of everything in terms of the bird.
Okay. All right. Okay, good afternoon. Welcome to the half review for the last half test. We've got quite a bit of ground to cover. Even though you get half credit for this section, you still almost twice as much work. So, anyway, let's get started. We're going to start with chapter 39, special relativity, and kind of take a close look at this. It's based on really two postulates. This first one is just the principle of relativity, and this has been around really since Galileo. He's kind of the first one that really introduced this. It comes from the idea of an inertial reference frame, and that's kind of harkens back to Newton when his first law, the idea of object at rest tends to stay at rest. If it's in motion, it tends to stay in motion in a straight line. The idea of an inertial reference frame is something that would be just moving along. Imagine an object moving with a constant speed through space and attach a coordinate system to it. And that would be an inertial reference frame. The idea of this is that all the laws of physics are the same in all inertial reference frames. So you can imagine you're going to get on board a rocket ship and take off, and let's say you packed away all your favorite physics experiments. You could pull them out on the way, and even though you were traveling relative to the Earth at some great speed, you could still be doing all your experiments, and they should verify the same laws of physics. So that's pretty reasonable. What's the weird one, and where all the strangeness from relativity comes in, from the second postulate. And that really came from the idea of electricity and magnetism, that when Maxwell put together his equations from electromagnetism and came up with being able to calculate the speed of light, it was all based on the experiment being done in some inertial reference frame. Then the idea is, well, how is it going to look from another reference frame? And there was a real problem with that. Lorentz actually got the right mathematics, but his reasoning was way off as far as giving a physical explanation. He didn't read the math right. Einstein read it and says, oh, well, this is simple. You get the speed of light, and it should be the same regardless of whether you're moving or not. But this leads to strangeness. So if you get some source of light like this flashlight, the idea that it's good, the speed of light, as I measure it here, would be the same for you if we came towards you with that light or retracted away. No matter how this source is moving, we always get the same value for the speed of light. So again, this is where the real weirdness comes in. So let's do what Einstein did is some thought experiments. Let's start with first one, the idea of a light clock. The idea of what we want to explore time. And the idea of a light clock is you could have something, and these are just sort of thought experiments, but they should hold. The idea that you could have maybe a flash of light. It would go out, bounce off, reflect off a mirror, and come back, and you receive it. And this is the basic timepiece of any kind of clock, whether it's a pendulum clock going back and forth. We have like this gets up here, maybe you call that a tick, and then it comes back here to a tock. So it could be going back and forth, tick tock, tick tock, tick tock. And that forms our basic clock. Now what is strange when we set that clock into motion? Laws of physics should be the same. So the idea that we would send that signal with a tick, that's going to send out a spherical wave that's going to go out. And if this clock is in motion, the mirror gets over to here just in time for the light to reflect off it. Angle of incidence equals angle of reflection. It comes back here and we receive it. That's a tock. So you can see that this light beam had a further distance to go than this one for a rest clock. Now with the speed of light being the same for both of these, the speed here is c, and also off this way is c and back down, we can look at this relationship between the ticks of the clock, or the timing of this. This one would simply be that, it goes up and back. Maybe I should put the 2 here. 2d is equal to the velocity c times the delta t of the clock. This is something we're calling the proper time for a clock that's at rest. More on that later. Then if we want to look at the time of this tick-tock on a moving clock, we would look at this, and really this is nothing more than the Pythagorean theorem. This distance, it's delta t over 2, the time of one of these tick-tocks, divided by 2. Half the trip here times the speed of light would be this distance. This distance here would be the same as it was back here. We could make that really anything we wanted it to be. And then this trip coming back is going to be the same as this one over here. So the idea, really, Pythagorean theorem, this is the hypotenuse, this. And we've got d squared. And it's moved over by the velocity in that same time that this goes up here is going to move over to here and then another one over to here. Again, you can see the Pythagorean theorem here. A little algebra, and we come up with our basic time equation, or we sometimes call this the time dilation equation. The delta t is what we call the proper time. That would be the time on a stationary clock or a rest clock. Quite literally, the reading on the dial of that clock. And then this would be the apparent time of this thing as measured by somebody that it's in motion with them. This relationship 1 over square root of 1 minus v squared over c squared is often, we call this gamma. This is kind of a shortcut to having to write this all the time. But you will see that the time for a moving clock is always going to be greater than it is for a rest clock. If you're looking for the fastest the clock's going to move is when it's actually at rest. Anytime it's set into motion, it's going to dilate or it's going to slow down. And as we go faster and faster and approach the speed of light, these triangles get bigger and bigger. And if you could, as you approach the speed of light, your clock will virtually slow down to, it would be 0, an infinite amount of time for this if it was, if you were traveling close to the speed of light. Okay, so that's this basic idea of the time clock. We'll deal with more with this as far as an example, but let's play with some of the other weirdness that comes to play with relativity. One is length contraction, which is really kind of the counter to time dilation. It allows us to make all of this thing fit together mathematically and have sense. Now, the idea that something is in motion, let's say this meter stick, where this meter stick is at rest relative to you, this is something we call the proper length. Anytime it's in motion, it's going to end up, we'll show you, be contracted. But let's, before I jump to that conclusion, let's talk about how you might measure something that's moving. The idea that you say, oh, well, a moving ruler is short, and you say, well, wow, how can you tell? This thing's whizzing by. How do you even measure that? The idea would be that if I wanted to measure a moving rod, as it comes through here, I know, say, what its relative velocity is. When it gets here, I could hit my stopwatch and it passes by, and as it leaves, I'll hit the stopwatch there. So I can measure that time. I know the velocity is the velocity of the stick. And I can say basically we're playing with distance is equal to velocity times time. The length of this stick would be the velocity times that time, and that would be a proper time. Notice I've chosen my clock. It's going to be at rest relative to you. So as this thing comes by and I hit it here and I hit it here, this clock doesn't move. It stays at rest. So this time we're measuring here is the proper time. Some subtle issues. Now, back in what we would call the rest frame, where the ruler or meter stick is as long as possible, we can take that point of view, but now from this point of view, if I have this this original length, let's see, this one seems to fit a little better, do this, and I'm going to look at this from this one's point of view. It's not this picture at all, but rather that it's the stopwatch. As the stopwatch is moving with velocity v, okay, I'm holding this one at rest, moving clock, it starts here, and it ends over here. I've measured a delta t, but from this frame of reference, I say, wait a minute, this is a moving clock. So we still are playing with distance is equal to velocity times time. That distance would be the proper length. The velocity is the relative velocity between the two. And the time would be what we would call is the proper time. Now, v times the proper time was the same as we had over here. That's L. So I can go ahead and replace that in with L. And what I've got here, and just rearrange this, L is equal to the proper length times the square root of 1 minus v squared over c squared. Or we could say 1 over gamma times the proper length. And this will give us this length contraction, where we can actually measure it. So the idea of length contraction and time dilation, they really work together, giving us a coherent view of nature, even though it's a little weird. It still doesn't have any inherent contradictions. So we've got time dilation, length contraction. You start to get kind of really weirded out by all this stuff. You start to question everything. You know, pretty soon, you know, velocity is equal to distance times time, or distance is velocity times time. Is that, you know, is that real or what? How about length contraction? We talked about it along the direction of motion. So if you start with something, a meter stick that's at rest, and you set something in motion, it will be contracted. The longest it is whenever it's at rest. But now what about moving horizontally, perpendicular to motion? Is it contracted that way? You might say, well, why not? Everything else is happening weird here. Why not? Now you can imagine we're going to take a meter stick, have a couple of them, and consider that one is going to be contracted. Just assume, I'm not sure what's going to happen, it's going to be contracted. What we can do with these meter sticks is imagine taping a marker on the ends of these things, kind of like these red markers. You could put one up here and one on the other end, and start to move them. One of them, let's say the S1, we're going to leave as it is, and imagine S prime is going to be moving in. Now I'm kind of assuming that it's contracted, so the idea is as it rips across here, those markers that are on the end of it are going to end up leaving marks on this stick, and it's going to go whizzing by. But it must be also consistent with the other point of view, that the S prime stick could be the one that's at rest, and the S1 is going to be in motion. So if that's the case, then this one should be contracted, leaving a red and a green mark there. So the S1 should be physically marked, and the S prime one should be physically marked. So, wow, which one is it? This came across here and marked that, but this one that passed on through didn't get any marks from this other one. Hopefully you can kind of see the argument. The only way this is going to work out is if the two red markers pass through one another, and that the stick is not contracted at all. So lengths are not contracted if in the direction perpendicular to motion. Hopefully you see that. A lot of what we do in relativity is we have to take these little thought experiments and come up with kind of a way of looking at this to reach some kind of conclusion. And we use a lot of the symmetry in this, that we can't have both of these pictures true. The only way they can both be true is if they are the same length and they do not contract. So, little taste.
Narrower, right?
Yeah, they would go, going this way. They are contracted this way, so good point. They would get a little thinner. Okay. Now, one that's a bizarre one is the idea of simultaneity. The idea of you could have, traditionally, they've done things like this. Usually Einstein called them, would use the idea of a railroad car. We can get a little more high tech. Imagine this is some cargo bay of some rocket ship traveling through space. And if we're inside that, imagine we're going to do a little thought experiment. Imagine we're going to have a little source of light. We're going to measure it out inside there. We're going to have this flash right at the dead center of this cart. And we're going to have two little light detectors on either side here. And so the idea is that this would flash, and that signal would go out, and being the same distance from the ends of these two signals should arrive, what we say, simultaneously at the same time, which seems very reasonable. Now, it gets weird when we say, well, let's take a look at that point of view from another reference frame that sits maybe outside the rocket ship. This rocket ship is now going to be moving with some speed v. It will be contracted, we know that. The flash is still kind of in the center of this thing, so it seems reasonable it should still have that symmetry right in the center. And then it's going to flash, but as this light is going out, this car is still in motion. So in a little bit, it gets to, let's say, here, just as this flash reaches it. So as this thing moves this way, the light comes here, and we would have what we will call an event. This happens first. And the other detector, which is moving away from this light pulse. This light pulse hasn't caught up to it yet. It's still traveling at speed c, and it will eventually get over here. In fact, as this whole thing moves off and gets over to here, finally the light hits it, and this detector reads it, and then we have this event, and it happens second. So we have two events that in one frame of reference happen at the same time or simultaneously. These two events happen at different times for another reference frame. Okay, this is bizarre and kind of hard to get your head around. So we've got these three principal things that where really all the kind of weirdness comes from. If you can get this idea that we have time dilation, and in turn length contraction, and then this overturn of this concept of simultaneity. Okay, yeah.
With the simultaneity, what would be the proper time for that? Like the proper timing for the light to hit each event? Like what would you say would be the proper time if you were going to say?
Okay. On this,
on your frame of reference?
It would depend on your frame of reference, and we're going to get into that, and we'll use the Lorentz transformation to answer just those kinds of questions. Lorentz transformation is going to take all these three and going to tie it into one. So the idea of tying this stuff together in a useful way is the idea of using these two reference frames. I'm going to look at something we'll call an event, and we'll look at it from two reference frames. We have just this blue one is just the x and the y. We'll call this the on prime frame. It's just a name. And if it's our point of view where we're at rest with it, another frame of reference, this green one, we'll call it the primed frame, would be perhaps moving in this direction with some velocity v relative to this other frame. Now, the idea that we're going to develop here is the idea that you might have something we call an event, a flash of light. It could be anything that you would want to call an event. It happens at a particular place in time, space. It has an x, a y, and a z for this point of view. And it also has some time that it happens for something like this frame of reference. This other frame of reference is going to read perhaps different values. We'll call this x prime, y prime, z prime, and also there's going to be a t prime. And so consider these are the coordinates of the event between two frames of reference. Okay, now what we'll do for this frame of reference, this is kind of a weird looking graphic here, I got carried away a little bit. The idea of thinking of a frame of reference, going back to this idea of two Cartesian axes, an x and a y, imagine that we're going to chop this thing up into a grid. These could be meters, you could have them any distance you want, and consider that at every point in space we have a clock that's going to be there. Now this comes into play with the idea of simultaneity. How do we get all these clocks in a given frame of reference to be reading the same time at the same time? The idea is we could have some kind of like a master clock or something that's going to trigger. We could start this at the origin, and then all these clocks, we could set them ahead. We would know how far they were from this origin, and we would set the clock ahead so that when we send a signal, it's going to be synced up with the rest of these clocks. So particularly synced up with this idea of a master clock here. So the idea is we set all these clocks, then from the master clock we send out a signal that goes out, and as it reaches these clocks it turns them on. And so since they're set ahead, they're going to get turned on. Anything that's gotten the signal are going to be all clocks that are now reading the same time. Now it's going to look very different from the other frame of reference, but the idea is that this particular frame of reference is coherent for this frame of reference. Again, come back to this idea of some event. The idea that those points that are lined up with this have a time associated with it, and that time would be measured relative to this reference frame anywhere in this reference frame. So that's sort of our common sense idea of what time is. We apply it to each one. Now the S prime frame, we would start our clocks the same way with that. However, it's going to be set in motion. So if the lengths are going to be contracted, times are going to be running slow, things are going to get rather distorted. But let's come back to that idea. First, anyway, that's the idea of a reference frame having all the clocks within that reference frame at least read the same time. Okay, the idea of the Lorentz transformation is going to allow us to take all these things and bring them together. So if I've got a couple frames of reference, the S frame is this blue one. It's, for our purposes right now, going to be at rest. We're going to have this green frame of reference is moving with some v, some relative velocity between the unprimed and the primed. If we have some event out here, and I'm putting this just on the axis, we show the idea of this. The idea that you see all these tick marks on the blue axis, that would be our normal meter sticks out here. However, the green one, since it's set in motion from the S frame of reference, these are going to be contracted and pulled together. So this contracted length would be, if this event happens for the green at x prime, that would be the certain numbers of tick marks on the x prime axis. But this is contracted, so I'm going to put in x prime times square root of 1 minus v squared over c squared. That would be this contracted length. Now if I want to get back and forth between x prime and x, I can look at this. This particular event, this is the x position of that. And then the x prime position, since its origin is moved over to here, is we'll just call that x prime. And so I've got that. The amount that this has moved depends on the time. When the origins coincide, that's really at time t equal to 0 for both of them, or at least at their center origins. Then this distance is going to be the velocity times the time moving this way. So now we just need to really look at this, this distance here, x prime times the square root of 1 minus v squared over c squared, that is equal to x minus vt. Okay, so this is very similar to what we did when we first started this course when we were looking at transformations. We didn't have the Lorentz transformation. It was just x prime is equal to x minus vt. That's something we call the Galilean transformation. Then I can divide through here, x prime, I'll divide by 1 over the square root of 1 minus v squared over c squared, and that is gamma times x minus vt. So this equation, this is our first Lorentz transformation, will tell us that if we have a particular event happening at x and t, we can put that x and t here, and that will tell us the x prime what that same event would read for a person in the green frame. Okay, so there's this kind of symmetry. Now, we could turn it around. We've got to keep in mind that a lot of times students will say, well, this is, the S frame is where it's really at rest. Well, it's not really at rest. We're just taking that mathematical point of view. We could equally well say that the green frame, the primed frame, is the one that's at rest. From its point of view, it stays where it's at, and the blue one is going to be moving in the negative direction with that same relative velocity v. Then we deal with this idea of this event out here happening at the green and the blue, and we want to get a relationship between them. Since the blue frame is moving, the x value for this one is going to be a contracted length. So we're going to have an x times the square root of 1 minus v squared over c squared would be that contracted length. Then we can look at the distance that it has moved since these origins coincide. It's v times t prime. All of this is from the primed point of view. And then we can again look at the idea that this distance, x times the square root of 1 minus v squared over c squared, has to equal x prime plus vt. So again, this is the Galilean transformation going the other direction. The only thing different, 1 over this, is this gamma. So we've got really both fundamental equations for where the event. Here, if I know it in the S frame, x and t, I can figure out what x prime is. Or if I instead know what x prime and t prime are, I can go ahead and get what x is. Now there'll be another Lorentz transformation that's going to be critical to what we're at, and this idea, just kind of point this, that we've got these 2 points of view. The equation 1 is the one for the on prime to the primed. We have this one was relating the primed to the on primed. And they both must be mathematically consistent. They should be effectively saying the same thing, but just from their relative points of view. So the idea is we should be able to, if x prime is equal to that, I could take this term and substitute it in for x prime. So I'm doing that just inside this equation. Take that, put that, and then go ahead, and what I want to do is solve for t prime. So doing some algebra, I'm not going to take you, all the steps are here. You can all piece it together. It's just algebra. Let's stick to the physics. I solve for t prime, and I get an expression that looks like this. This is the Lorentz transformation for time. So if I know this event, the x and the t, when it happens, I can go out and get the t prime, where the time that it would be for the green frame of reference or the primed frame. Also, I could take this one, again, just symmetry, this, and end up substituting into this, and then solving for t, the time in the unprimed frame. And I get this as an expression. So both of these are true. Now, there is some weirdness in here. Time, look at what time depends on. Maybe I'll choose, could use either one of these. Maybe I'll do this one. This time, if I bring the gamma through here, gamma times t, this would be the proper time in, let's say, the blue frame of reference. That should be the dilated time. This other term is actually depends, the time here depends also on the position of that event. This has to do with the idea of the simultaneity, that time is different if the x value is different. So in a sense, this ties together time dilation and then also well, we've been using length contraction to get this, but then it's also the idea of simultaneity. And so this will do the math for us and answer those tricky questions as far as where did it happen, when did it happen, for any frame of reference, or at least between the two that we're talking about. Okay, okay, so this is kind of a summary out of the book. This was really because y prime is equal to y, because lengths do not contract along the direction of motion. We have all our motion in the x direction, and same thing for the z is. But certainly for the x prime, we've got this relationship, and then for its corresponding time of the event is that expression. And we can go from either on-primed to primed, or from primed to on-primed. You'll notice that there is a symmetry between these. One thing that we have done for this, let me just back up a couple slides. For our basic idea, oh, wait a second, I'm going the wrong way. This is kind of a simpler picture here. One thing for all of our equations, we are going to assume that this is like the plus x direction, and it's plus for the x. It's also plus for the y. The relative velocity between them, v goes in as a plus if it's the prime frame. This is where people get the idea, well, this one's in motion and this one's at rest. This is only the point of view from this one at rest. As soon as we change it for this one being at rest, the relative velocity of this one is going in the negative direction. So there's a little bit of
John.
Yeah.
She has a question.
Oh, thank you.
Yeah.
On the more specific one, like two slides before that.
Mm-hmm.
Okay, on the first one, I noticed, I'm just looking at the color coding on the top, the V. Should that be
Oh,
green?
yeah, I would, yes, I would. Well, actually, it could be blue and green.
Okay.
Yeah, I would change the color too. I did it with a marker, and I looked at that too. Yeah, you could say it's the green one is moving with speed v, and then this one is the blue one is moving in the negative. Okay. Now, yeah, it is confusing. That's one of the things with relativity. You got this idea, you got these different points of view, and you can start to see them all, and you kind of short out. It's easy to get really dyslexic with this, you know. Where am I? So that's where. Whew, okay, yeah. Which point of view are you taking? Notice that these are the same basic form. The only thing different is this negative sign in this one. This is positive. So V is considered, and we put a number in here. We put that in there if that's in the plus direction. The only thing different from the other frame of reference is that it's V is traveling in the negative direction. So if we put in a positive V for this one, this is we're going to have this negative sign. If I put a positive V in for this one, this is going to be positive. So the only thing really different between these is that their V's are different. One is in one direction, V is in the other direction. So if this is plus, this would be minus. Yeah, I'm having trouble saying this. Oh. hopefully this makes a little sense. When you see this, you can also realize this V again. I've got a minus sign for the primed. It's a plus sign for the unprimed. These are just opposite in signs. This can help you remember these, since you have to remember a lot for your exam. But these are your basic Lorentz transformations. Okay, now it also works for deltas. You can go, delta is, final minus initial for all of these terms. And it's not hard to take those Lorentz transformations and take what was an x prime and make it a delta x and delta x and a delta x or a delta t. That's going to be kind of your difference between two events. And this is going to be useful when we look at velocity, the velocity transformations. Okay, the idea is, what if we have something moving? Now, keeping all this stuff straight, I've got an unprimed frame. This is the S1, where, at least for doing the math, we kind of think of it as at rest. And that this green frame, again, I should have colored that green. This frame of reference is moving relative to it. And if we want to measure the speed of, let's say, some object, like another rocket ship, something other than these two frames of reference, we can choose a couple of events. Imagine we're going to time this. We're going to hit our stopwatch here, and it goes some distance, hit our stopwatch. And then we get our usual velocity is delta x over delta t. So that idea is basically the same. Now, for the Lorentz transformation for, let's say, delta x prime, this is that expression, and we also have for delta t, we can take these two and say, well, this u we use for the speed. Keep in mind these v's we reserve for the idea of the speed of the moving reference frame. U represents the velocity for at least a third object, or some other object that's moving in both frames of reference. We can relate their velocities. So u sub x prime is delta x prime over delta t prime. That should be reasonable. So we're just going to take that expression, divide by this expression. The gammas go out. We have something relatively simple. Then I take both numerator and denominator and divide by delta t. So that one goes away, and I have a delta x over delta t and another delta x over delta t in the denominator. And I can complete that. Delta x over delta t is what we'll call the u sub x. That's the velocity in the x direction. That's the u measured according to the unprimed. So I've got u sub x minus v all over 1 minus v times u sub x. Okay, we can do something similar for the idea of the unprimed here, that we know what the primed terms are. We can take that, which is that, divided by this. The gammas are going to go out again. Very similar to this. Look at these two expressions. They are almost the same. Again, the only thing different between these two frames of reference is the velocities would be in different directions of the frame, so we can take either point of view as being at rest. So this has got a minus here. Notice it's also got a minus there, and a plus, and this is going to be a plus. These are both going to have the same sign to them. Now, something that can really help you in doing problems here. The very top part of this, let's see, I think I've got it. Okay, just kind of summarize it a little better. This is just right out of the book, so we can see the formatting here a little clearer. Again, this is minus, minus, plus, plus. What you can do is, if you sort of ignore the denominator, this up here on top is the Galilean relativity. So this is sort of your common sense point of view. And then to make it relativistic, we put all this stuff in here as well. And of course, we We derive that. You don't have to derive it, but certainly you're likely going to have to be able to use these 2 points of view. Okay, let's see. Yeah, now the book also deals with velocities like in the y direction or the z direction. They follow kind of a similar kind of derivation, but usually he doesn't go down that route, and we haven't been doing any homework problems that relate where you need to do these. So I would file these away. They're not difficult to show. They're a little easier to show than these guys. But this is primarily the ones we're going to be using like for the exam. Okay, I'm rattling through this. I hope this is making a little bit of sense. Relativity is something you really need to spend some time on if you're going to get it. If you really dig it, summer's a good time to just sit back. You got to think through it and think through the paradoxes, and then it starts to come to you. It's very kind of counterintuitive to begin with. Okay, let's do a problem. This is a homework problem. You recognize it? It's kind of it illustrates these ideas pretty well. So let's just take a careful look at it. Okay, we have a Klingon spacecraft moves away from the Earth at a speed of 0.8 c. So here's the Klingon. It's moving away. The Starship Enterprise pursues at a speed of 0.9 c towards the Klingon ship. So that's sort of the picture. Observers on the Earth measure the Enterprise to be overtaking the Klingon ship, a craft at a relative speed of 0.1. Okay, that makes sense, right? If you're trying to get a picture of this first part of it, you can reason kind of common sense. If you were traveling down the freeway at, let's say, 80 miles an hour and somebody else is coming up at 90 miles an hour, they're gaining on you by, 10 miles an hour. So this is kind of a common sense look. If we want to get over and get it from this other point of view, we're going to have to use our velocity addition equations. So this is where, now the book, you don't have to do this, and I think it's important that you can see that you can do this a number of different ways. They more or less prompt you in this problem and say, well, call the Earth frame the S frame, okay, and that's a reasonable one. It would be more arbitrary where you call S prime. We could have made this our S prime frame, and then this would be our third object. They kind of prompt you in the problem here to say, well, this is the S prime frame. So we want to get back to this one. We know what U is. That is the speed of the Enterprise relative to the Earth. Okay, not the speed V of the frame itself. The Klingon ship is making this the S prime frame that's moving with this particular velocity. Now, if we want to get at what is the speed of the Enterprise relative to the Klingon ship, we know U, and what we're really looking for is really U prime. So that's where we want to make use of of the velocity transformations. We can feed things in. U sub x, that would be this guy, U, 0.9. Minus V, and we would just leave that minus sign there. V would be considered positive since it's going in the plus direction, so this is going to be 0.8, just as is. And then we're going to have these terms, that's going to come in here, that's going to be the relative speed, times U sub x, which was 0.9. Notice we are times c, and we're going to divide by c squared. So this c, and those c's are going to go out. And from there, the math is pretty simple. It's going to be then u prime is going to be 0.357 c. And this would be the speed of the Enterprise as seen or measured by the Klingon ship. So this is positive. So the Klingon ship sees that the Enterprise is approaching in a positive direction. That's positive. They give a little twist here with what speed is the Enterprise overtaking the Klingon ship as measured by the crew of the Enterprise. So we really want to get back to this point of view. Those two speeds should be relative. The idea that from their point of view, if you've got a seat on the bridge here, it's going to look like the Klingon ship is backing into you. At 0.1 C, or excuse me, at the negative of this. So that would be following that point of view. So, okay, hopefully you got that and you can think of that. We do have to watch these signs. Again, we're calling this the plus direction for both frames of reference. Yes?
Does the 0.1 C in the problem exist purely to confuse, or is there...
That's going to be up here when we do this. We're going to get a 0.1 C. So that, again, that raises the issue that is sort of the common sense point of view. And if you cover this up, it's a good way to check your work. Does this make sort of common sense that the Enterprise is approaching at 90 miles an hour minus the speed that he's trying to get away at 80? So this can help you, and then whatever sign you come up with here, that's going to end up echoing that sign down there. So that can be little checks to see if you've messed up. Okay, a good chance you're going to get problems like this. So here's another one from the test. This is from a test. Consider two inertial reference frames, S and S prime, okay, where S is moving to the right, okay, so that means that at 0.6 C, so we would call that a positive value. It's in that direction. Now we're starting to get a little tricky here. A stick, proper length 1 meter, so it's a meter stick, moves to the left of the origins of both S and S prime. So it's coming back in the negative direction. The length of the stick is 50 centimeters as measured by an observer in S prime. Okay, and then determine the speed of the stick as measured by the observers in S and S prime. So, wow. Okay, now, who's doing the measuring? This idea he's going to measure a half a meter here. This is really the primed frame of reference that is making that measurement. And we can say that, well, that's length contracted. Originally, its proper length is 1 meter. Its contracted length is a half a meter, and from that we should have this 1 over the square root of 1 minus v squared over c squared. The v is going to be, this is going to be u prime, since it's measured relative to the primed axis. And I can go ahead from this and I can solve for that. Now when I solve for this, you're going to have a square root there. There's going to be a positive value associated with u prime. I stuck in this negative sign because all we're going to get from this is the absolute value of the speed. So the stick could have been moving this way. It does explicitly tell us in the problem that it's moving to the negative direction. So whatever u I get here, this 0.866, I need to stick in the negative. So you have to have enough sense that that's going to be your sign that you would use. And that would be the speed of the stick relative to the S prime axis. Okay, now once I have that, then I could go back and say, well, now what is the speed of the stick relative to the, the length of the stick? Determine the speed of the stick as measured by both observers. What I've got here is what have I got here? Okay, we got the contracted length, so we got u prime. What we need to get is u, which would be the speed of the stick relative to the unprimed axis. So I would use this of the Lorentz equations. Again, this is u is going to be a negative 0.866. V is still considered a positive 0.6 C. And we stick in the rest of the numbers and complete that. And we end up with u is going to be minus 0.55 C. And that is going to be the speed of the stick relative to S. So again, we got the speed of the stick relative to u, speed of the stick relative to the s. It's still negative because it's headed towards the origin of both of those, so that should make sense. And that would be our result. Okay? So you got to do a few of these to kind of get the hang of it. Once you do, they're not too bad. He can get a little trickier. Something with the relativity. The idea is if you're doing the physics from some frame of reference, and you do it with just information from that frame of reference, you do the problem just like you would like on a 121 exam. The only time you need to really watch relativity and pay particular attention is when you're taking information from one frame of reference and taking it into the other frame of reference. Okay, now this one, a physics professor on Earth gives an exam to students who are on a rocket ship traveling at 0.85 c relative to the Earth. Okay, so they're going to be zipping along. The moment the ship passes the professor, she signals the start of the exam. If she wishes her students to have a time of 55 minutes, this is time on the rocket to complete the exam, how long, Earth time, should she wait before sending a light signal telling them to stop? Now, this whole thing about times and proper times can get confusing. You want to consider that there's clocks everywhere. The professor has a clock, the students have a clock, clocks everywhere. And so when you're talking about proper time, you first have to say, well, what clock are you talking about? And then if you are talking about a particular time, like the professor, you're timing that. That clock is at rest for her, not for the students, but for her it's at rest, and doesn't move. And so this is really the proper time for this. Literally, the reading on the dial of the clock is the proper time. Okay, now the students are going to take off. Now, the only thing that we're going to use relativity for is the professor, with her clock, she knows that the clock on board the spaceship with the students is going to be running slow. Okay, for her perspective, from here, that's a moving clock and will run slow. So we would use time dilation for that. She wants to give them, now this is the 55 minutes is the proper time, not for her clock, but for the clock on board the ship. That's 55 minutes. We can go ahead and get this time, 104.4. That's the dilated time that the professor will see. And so her clock back here, she should let kind of a delta t, as she starts the exam, she wants to stop it at 104 minutes into the exam. And say the test is over, and the students will have had in their frame of reference 55 minutes. Okay, so now from here on, this is the only piece of information I need from that other frame of reference. The rest of this is all from her point of view. She's doing the figuring. What she wants is, she wants to know how the exam gets started here. She gets out to here where we want to end the exam. Their students are way out in space, and she wants to stop the exam, so she's going to send a signal from the Earth out to the spaceship saying basically, okay, when this gets there, stop the exam, turn in your papers. Okay, so we need to figure out how far this spaceship moves before the end of the exam. This distance is the students are traveling at this velocity for a time of 104 minutes. That's going to get out here to be 88.75 minutes is the time she has to wait to send this signal, and then this time for the signal is going to be distance is equal to velocity times time, or distance over time. we've got the distance was this 88.75. This is minutes times the speed of light. So this is, consider this like a light minute is how we could say that. This many light minutes. And this is going to be the time that it takes just for that signal to get there. So what she comes together with is she knows she has to give them 104.4 minutes, but she has to send that signal that's going to take 88.8 minutes just to get out to them. And we take this difference and we see that that's 15.6 minutes. So that means that when she's here, they go whizzing by, start the exam. She waits 15.6 and then sends the light pulse, and the light pulse gets there just at the time of the end of the exam. So that's what we come up with. So this was the question. She wishes her students have the time of 55 minutes in the time of the rocket frame. How long, Earth time, should she wait before sending a light signal telling them to stop? Okay, so this is how far. Now, what's kind of good in this experiment? It's kind of cool to see that we're taking her point of view. This is the rest clock, and she says that the students, the time is dilated or running slow. Now, classic to what we call the twin paradox, we could turn this around and say, well, shouldn't the students see the professor's clock running slow? Okay, what's wrong here? This just isn't making sense. So we can take another point of view. We can take the student's point of view and see what's happening. The idea that they would be effectively staying at the same place. So the rocket's here, and it's really the Earth that's traveling in the negative direction at 0.85 c. So this would be the start of the exam. The Earth is flying off at 0.85 c. At some point, it's going to send a signal, and that distance here is going to be the speed, 0.85 c, times, I'll call it t1, the time for the signal, for the Earth to get here, and the time that she needs to send the signal, t1. And then there is this signal that's got to go back to the students. It would travel the same distance, but it's going to be traveling at c, the speed of light, times, I'm just calling this t2. So the idea is this distance here has to be the same. So again, this time t1 is the time for the Earth to move out here, send the signal. t2 is the time for that signal to get back. And then we're going to end up saying the total test is going to be 55 minutes times t1 plus t2. So imagine the students are going to just kind of help her with her numbers here. She's a little slow from their point of view. t1 again is the time for the signal to get sent. And so I really equate this distance out to here when she sends that signal and the distance or the time that it takes to get back to her. I can solve for t2, it's 0.85 t1. I can go ahead and substitute that in. So again, it's just the sum of those two times. One thing you want to think, I'm kind of bumbling through all of these, but really so far I haven't done anything from relativity. All of this hopefully gets a little confusing when you get a look at all this stuff, but these are really how we would do it if we were in 121. So I go ahead and solve for t1. I get 29.73 seconds. So that's what the students are saying, that she should wait to send the signal. And then that would be then 29.73 minutes into the exam that she has to send the signal back. Okay, now from the student's point of view, the professor's clock should be working. Now consider all of this was just the students, got out a piece of paper and they're working through the details and say, okay, you got to wait this long. But for them, they say, but wait a minute, she's a little slow, remember? What's going to be her proper time here? So the students come up with this, and they say, well, what should be the reading on her clock? That it's her clock that's running slow, not ours. So we go ahead and put that in, and what we're solving for is really the proper time. And so from that point of view, we get the same proper time. Again, there's an agreement from either point of view that that proper time for her sending the signal is that 15.6 minutes. So again, we've got from method 1, we had the idea of the professor's frame of reference, where the student's clock was the proper time and they were running slow. And then we can also look at it from the student's point of view, if it's consistent. And we have them saying, no, it's the professor's clock that's running slow, but we get the same answer. So you really can take either point of view. This thing with, they call it in there with a twin paradox is a real classical problem. Okay, there's another homework problem that illustrates a lot. It's the very last one. Anybody get it? All right, good for you. Okay. Anybody even try it? Okay, this is kind of fun. The idea that suppose our sun is about to explode. Okay, in an effort to escape, we depart in a spacecraft at point 8C and head towards the star Tau Ceti. So we've got the sun, and we've got this distant star Tau Ceti. We're going to assume that they are at rest relative to one another. Okay, and then now the astronauts are going to be doing the traveling. When they reach the midpoint in the journey from the Earth, we see the sun explode, and unfortunately at the same instant we see Tau Ceti explode as well. Okay, so we see them both go off. Now just think of this. We have these, this isn't the picture for this. I should have drawn a separate one. It's a fairly simple one. The idea that you have the sun and Tau Ceti. The sun's going to explode. Tau Ceti is going to explode. The two blast waves would come, and they should meet right in the middle. If the astronauts are right in the middle, when they receive both ones at the same time for them, we'd have to conclude that those events, those two stars had to explode at the same time. Most people don't have too much trouble coming up with that point of view. But what they want us to do is take the point of view from the astronaut's point of view. They're going to get the blast at the same time. Now, the only thing we're going to use relativity from, most all of this gnarly looking stuff is really just classical. The only thing I really need is that the speed of this is 0.8 c. We can get the gamma factor for that, so we just plug that in and get gamma. I get a 1.67 for gamma. Now, as far as the astronauts, everything we're going to do is kind of within their frame of reference. The only thing we're going to bring in is, instead of the sun and Tau, which were 12 light years apart, the astronauts, as they're about to blast off, this would be the astronaut going to take off, these would be contracted to 7.2 light years. I could write it times c times years. The speed times the time. So that's going to be a shorter distance between the sun and that distant star. Okay, now this is when he's first taking off. Of course, they don't know they're going to leave. The sun's going to explode. They don't know yet about Tau Ceti, but in their mind, it's still out there, and we're going to go for it. So the astronauts take off, but now from their point of view, they just stay at the same point. So I'm kind of going to move through this in kind of like a slideshow. So this would be where they take off. From their point of view, it's the sun that's moving at 0.8 c, along with Tau Ceti moving at 0.8 c, both moving in this direction. So the idea, let's look at the sun first. It's going to be moving off, and at some point it's going to explode. And it's going to start to send the signal back. Again, this is just purely classical. This is going to be the speed, c. It's going to travel the speed of light times this. I have t sub s for the sun, time for the s for the sun to explode. It's going to reach back here, and this blast is going to get back to the students. The students are inside this rocket. Now, in the meantime, as this signal comes back here, the Earth has moved. Right now it's ashes. The sun and everything blew up, but those ashes in the center of mass would still keep moving in a straight line, and at the halfway point, they would have been half of this distance. 7.2 should be 3.6 light years across here, and the ashes, of course, are traveling during the time for this signal to get back there, are traveling at 0.8 c times that. Goes out this way. So we can look at this, and this is just a simple relationship that this total distance, 3.6 light years, is equal to 0.8 c times this time the signal was sent, and then this distance that the signal actually traveled was the speed of light times that time of the signal. So we put these two things together and solve for the time of the signal, and this is going to be 2 years. So basically after the Earth has left, or back here, 2 years later it's going to explode, and then again this is going to send the signal this way. The Earth goes on. This is going to be 3.6, and equating that, we determined that after they left, the sun blew up 2 years in the past. Okay, so that's this, but now we also get the ominous news from Tau Ceti in the form of a blast from that explosion. So consider this: when the students are here, Tau Ceti explodes. It was moving along with the sun at 0.8 c, so it's going to explode and it's going to send a blast wave. That's this blast wave from here all the way back to the origin. C times tau of t sub tau for Tau Ceti would be the distance that light flash would travel. The ashes from Tau Ceti that blew up are going to be moving, or at least their center of mass is going to move at 0.8 c times the time that it takes for that signal to arrive. And then all the ashes are sitting here, and since it was the midpoint of the journey, it should be 3.6 light years to here. And now we can do the math on that. For Tau Ceti, this total distance, c times t sub tau, should be equal to 3.6 light years, plus this distance is going to be 0.8 c times the time of Tau Ceti. So we've got two terms there. Do a little math, and we come up with t of Tau Ceti is going to be 18 years in the past. So that's even before they left. So that's kind of a surprise. Again, the only part that I used in this whole mess that was relativistic from the Earth Tau frame of reference, this was 20 light years. I guess I did use for gamma, but basically I'm just using length contraction. The point of view of the astronauts is these are physically closer. That changes the numbers dramatically. Again, things that happen simultaneous in one frame don't happen simultaneously in the other frame. Wow, okay. Now, if those that are kind of mathy types, you can do this problem pretty nicely with the Lorentz transformations. We got the time. We're using the time, the on prime for the Earth frame. So the idea that we first reasoned that two explosions should happen at the same time, the delta t between them should be 0. Minus, we have the relative velocity over the speed of light, and delta x would be the distance between those two events. And that distance should be, as it was originally, 12 light years. And then we can use this to solve for the delta t. The time between the explosions should be a negative 16 years. So tau exploded 16 years before the sun exploded, which is the same thing we would conclude here. This is 18 minus 2 is 16 years difference. So if you're clever to use that, you can sometimes take these gnarly problems and really cut them down to size fast, as long as you know what you're doing as far as sticking in numbers. Okay, so those are relativistic kinematics. I would say likely you will get a problem with that on the exam, or a very good chance. You definitely want to be ready to do that, so I did a few examples. Now there's some other stuff relating to relativity, relativistic dynamics, momentum. This is not really derived for you in the book at all. They just give it to you. There are some thought experiments that Einstein used to come up with this, so it's not like it's coming out of nowhere, although it certainly for you it is. They also did the definition of force is going to be the time rate of change of the momentum, so this is a little different than F equals ma. These two would be the same as long as the mass would stay constant. I better steer out of that discussion. Just take this as a given. And then the work energy theorem, like we did back in Physics 121. We did the integral of the work was equal to the change in the kinetic energy. So by integrating this and coming up the work done, we can come up with the kinetic energy of the particle. Okay, so it's looking a little hairy, but this is again just coming out of the math. They do it in the book if you're curious. I don't want to get into doing it now. We can break this thing up. Well, these are just factoring out some terms. Maybe I'll factor these out, gamma minus 1. And actually, we want to look at this idea of total energy. The idea that the total energy is going to be the kinetic energy plus what we call the rest energy. That rest energy is just, this is where the old E equals mc squared comes in. Something at rest has some intrinsic energy for it. And so I can go ahead and put in the K and subtract the rest mass. Anyway, you could check the math here. I'm kind of bumbling along here, and I didn't lay things out as well as I should have. The total energy of something that is both kinetic and rest mass is going to be gamma mc squared. So this is sort of like E equals mc squared, only if it's in motion, there is this gamma factor that comes into play. But certainly you can sort of remember it, that E equals mc squared, but that was related to the rest energy. Usually problems, if he gives you anything along this line, is basically going to be plug and chug kind of stuff. So we've got some of these, and this is, you can see how he's broken it down. So again, he's not going to have you derive any of those, but you might have to plug things in. So what is the kinetic energy of the spaceship? It's gamma mc minus mc squared. That's we just factor that out. So that's the kinetic energy of that. We can take the, well, you can do the math. Essentially, if you can understand this, it's just plug and chug as far as putting these numbers in the expression to get the term, the kinetic energy. That would be in joules. P is going to be the momentum of the particle. Again, just plugging and chugging with all the numbers. We're coming up with this. You can check this out on your own. Hopefully you're good. Then part C, let's see, if the kinetic, he's getting a little trickier here. If the kinetic energy in part came from the futuristic engine that converted mass into energy, how much energy would be converted into kinetic energy? So the idea, the energy gained is going to be the mass energy lost. Okay, that's going to be equal to mc squared. So that's how much taking that rest energy, converting it to energy to give you that kinetic energy, and then solving for that mass. We take that kinetic energy divided by the speed of light squared. Ooh. This should have been squared. Okay, I'm not sure. This might be the right number, and I just didn't write it down right. Yeah, definitely put a question mark here. I'm just realizing that. And then part D, today's rockets launch with 90% of their initial mass as fuel. Only 10% of their mass is payload. And these are just giving you a little history here. They typically get to a speed of maybe 17,000 miles an hour. Which is, as far as the speed of light, is very small, so we don't really even need to use relativistic equations. However, he's giving you now another question. If a futuristic engine converts 90% of its initial mass into kinetic energy, okay, what would be the speed of the payload? So the idea is the kinetic energy should be equal to this mc squared, the rest mass energy. We want to figure out how much mass we want for fuel. He does tell us that the final mass is going to be the 10% of that initial mass is going to be the payload, and we have 0.9 c is going to go 0.9 times the mass is going to go into the fuel that's going to fire this thing, and so solving for gamma minus 1, just moving some terms around, you're going to see that initial mass, he doesn't say what it is, that cancels, c squared cancels, and we end up, well, you can do the math here. I end up with a gamma. I have to use the gamma to get at the velocity. So we'd be traveling at 0.995 c, the speed of light. These are things, I'm bumbling through this, but go through these and convince yourself that it's true. These are just good examples of how these things are. And typical of what he might ask is just some kind of plug and chug if you're going to use any of these equations from, we say, relativistic dynamics. Okay, so that's relativity. Boy, that's taking a fair chunk of time, but that's probably the most difficult material you're going to have as far as test questions. Most everything else, the thing is with most modern physics, it's either so complicated as far as doing the problems and so difficult that he couldn't possibly ask you any questions, and then or they tend to be just kind of real trivial like we were looking at here. So all he can really ask you on this stuff and this new stuff is really trivial kinds of questions, which are pretty much plug and chug. Again, that's why I'm prompting you that relativity, relativistic kinematics, is likely where he'll look to give a tough test question. Okay, now I believe he went through, this is, relativity was chapter 39, this is chapter 40. He, believe, went through this I was looking at notes, covered most of this chapter, but I think you can see probably from his discussion it was probably pretty brief. It's really done more in historical overtones. And kind of how did we even get to where we're at today? And it usually starts here, the idea of Max Planck. He was trying to understand what really thermal radiation. We had this earlier when we were talking about thermal. The idea that the power radiated is this sigma times the area times the emissivity, just some constant for the surface, to the fourth power of the temperature. We can look at things, this light that's coming from this source. It's got some temperature. Anything with any temperature at all going to come out. Something like the filament of the light bulb, the actual color of this and this, if they are the same, they're going to be really at the same temperature. the idea, this is a continuous spectrum, so it's across the wavelength, so we have wavelength here, and relative intensity, it's going to go up, it peaks at some value and comes down. The peak is going to move to shorter and shorter wavelengths as we go to higher and higher temperatures. This is something called Wien's displacement law. Whether he's going to have any of this, not likely. What Planck did, he really struggled with this whole problem for about 19 years, and there were some things that were nagging, and he kept picking at them. And he got to the point where he had come up with a way to reason, this is both from physics as well as math, what the intensity curve should be. It was fitting these intensity curves very well, but he had one nasty thing happening here, for his point of view, that the energy inside the walls here, as it's kicking around within here, is being radiated and absorbed together, and always radiated and absorbed in a product of Planck's constant times whatever the frequency is. This is these chunks of energy. The energy, in a sense, had to be quantized in order to make this work. From this experiment, he came up with this constant. He didn't call it after himself, but he had this constant here that seems to work with the data. When he presented his paper, he was actually hoping somebody could make some sense of it, because he thought it pretty much just a fudge factor. Einstein, when he saw it, he thought there's something deeper here, that there's more to this idea than just this one property of thermal radiation. Or this is called thermal radiation. It's also called black body radiation. We say, wow, why is it called black body radiation? The idea is if we want to measure the light coming from something with some intensity, we don't want any light from the surface of this. The surface, outside light might come and hit on the surface and reflect off, and we want to be able to just sample what's inside here. And the idea that any light coming in would come around, would bang around, it would be absorbed. And so typically you also see it termed in some literature as being cavity radiation. That's the idea in here, very much like inside the coal, where we want to look at that light coming out from here. And we can be assured that it's all coming from inside here, from the thermal effects. So again, I think for our point of view, calling it thermal radiation is probably more descriptive, but you will see black body radiation, also cavity radiation, and so just keep in mind that. Einstein took this idea, though, on another direction. He went with the photoelectric effect. He's saying, okay, I think I can use this Planck's constant here and indicate that this idea that this bundle of energy was not something strictly between the walls of the cavity. This is what Planck thought. He says all this is going on, and it was some property of the emissivity of this surface inside here that we're worried about, and this is it. But Einstein really took it one step further. He says this piecewise or quantized nature is actually in the radiation itself, not just coming from the walls. And so he took this idea that light, the energy of a photon, is Planck's constant times the frequency. That energy is more fundamental, and he didn't coin the name photon, but the idea of making the photon a bundle of energy, and that bundle of energy is Planck's constant times the frequency. Now, this experiment we're going to be doing in the lab this next week, and this gives us another way of getting at Planck's constant, which again is an experiment very different from what Planck did. So this is where Einstein's looking for more insight and meaning to this. Now the idea is this, that you can shine some light in, and we've got them in an enclosed tube. Just as it comes through here, it's going to strike a metal surface. And as that light comes in, it can eject electrons that are going to come off with kinetic energy, going to come flying off of this. And in the lab, we'll measure that kinetic energy with what's called a stopping potential to keep it still. But let's not get too much into the details here. But the idea that there's a photon of light coming in, this packet of light, minus some energy, this is what's called the work function, the energy required to pull off an electron from the surface, is going to go into this emitted electron. So, whoa, okay, see if we can not get too lost in the details here. The idea that this is the energy of the photon minus the work function is the energy required to pull off an electron. That difference is left, what's left over is in the kinetic energy of the electron itself. And this is the maximum energy. The work function is really the minimal energy to pull something off. In reality, the light can go in deeper than just the surface of the metal, and when it goes deeper than that, the work function increases. So that would lead to a smaller kinetic energy. So the largest kinetic energy happens right at the surface where this photon comes in and strikes that surface. Yeah, there was a question. Okay. Okay, if we look at this now, the idea that the higher the frequency, the more the energy, and the more the kinetic energy. And so the idea that if we have some different metals, here's a metal here that, let's just do this one. At some frequency, it's sometimes called the cutoff frequency, this is where the effect would just start to happen. The idea that the cutoff frequency is where where this would go to 0, and then HF is equal to this constant here, and that frequency where that's at would be what we would call the cutoff frequency. It can't go in this region here. All this kinetic energy is always positive. These electrons come flying off this surface, and as we go up in frequency, the energy of that goes up. It's a linear relationship, you can see, it's a straight line, so the math is pretty simple. As frequency goes up, the more energetic photons come in. We're going to get more and more energetic electrons coming flying off of this thing. You can use this with just a single electron coming off and starting to build kind of an avalanche. So you can take a single photoelectron and use it to trigger a cascade of things happening so that you can actually get a measurable output. Kind of like a Geiger counter uses the same basic idea, where you hit a little photon in and an electron comes flying off. Okay. Okay. Again, I think we'll maybe hear more of this in this coming week. You will in the lab where we actually do this, and hopefully it'll make a little more sense to you. Okay, as far as doing problems, most of them are kind of plug and chug. Here'd be a typical example. Aluminum has a work function of 4.2 electron volts. Let me deal with that. And if UV light, lambda is equal to 208 nanometers, and that hits the aluminum, what is the speed of the ejected electron? Okay, it gives you the mass of the electron. And we've got this, again, this is our basic relationship. Typically these kinetic energies are not relativistic, so we can go ahead and use classical mechanics, 1/2 mv squared. as equal to this. And then we want to solve for, we're going to end up solving for V. You can stick in the numbers. Now he gives you this 4.2 electron volts. Now we need to convert an electron volt into joules. Now, the conversion for that is that I think basically just give you that if we want to, when you hear the words electron volt, think of energy, and the relationship, if we want to turn it into joules, we have to have 1.6 times 10 to the minus 19th joules for every electron volt. So we would multiply that. Those of you that have Physics 122, you recognize 1.6 times 10 to the minus 19th. This is the charge of an electron. So an electron volt is the charge of an electron times the voltage. And we want to turn that into joules. So this conversion is a little clumsy. From the rest of that, we go ahead and solve for the V, the velocity, and again, that is just math from there. So we are making use of this work function. I thought I had put that in earlier. Yeah, this got it on a note page. Actually, I had this a little earlier, and I decided to put it here. Well, consider this as just given. We can make more sense of this, but just remember that. If you see your energies in terms of electron volts, you just multiply by that. Okay.
Hey, Don.
Yeah.
You take like a 5-minute break.
Yeah, good idea. I could use that too. Yeah, excellent. I think that's a good time to do that. Yeah, let's take about 15 minutes, and you've got some coffee over here if you'd like.